Hello, my name is Gary New. On behalf of myself and Michael Kercher, we thank you for the opportunity to share our experience with our data center design, the different systems within it, and the lessons learned along the way. I am the operations manager of the NWSC, located just outside Cheyenne, Wyoming. I have worked at NCAR for nearly 20 years and was heavily involved with the design and subsequent operations of the NWSC. Michael Kercher is the primary author of this paper. He is the NWSC Central Utility Plant, or CUP, supervisor. Michael was hired very early in the construction process of the NWSC, so he has been heavily involved in the construction and operations of the NWSC. Michael specializes in building automation. He and his team have done a phenomenal job of fine-tuning our building automation system in partnership with our building automation vendor, Johnson Controls, as this paper will explain. Construction of the NWSC began in June of 2010 and was completed in October of 2011. Our first supercomputer, Yellowstone, was brought online in October of 2012, which gave us approximately 1 year to fine-tune the building systems, which I would highly recommend to anyone building a new data center. As you can see from this slide, the jump from Yellowstone to Cheyenne, which was named in order to commemorate the city of Cheyenne, Wyoming's 150th anniversary, gave us nearly 4 times the compute power for the same power consumption. Both systems ran in parallel throughout 2017, which made the facility power usage effectiveness very happy. We exceeded the design PUE of 1.08. This is a quick slide on comparison between typical data center design and the NWSC, and addresses the common question we are asked: why Cheyenne? Through common regional weather conditions and system component considerations, the NWSC is an extremely efficient data center and has received global recognition for its design. This slide shows some of the specific criteria that was followed throughout the design process. If anyone has any further questions about our design process, feel free to contact us and we would be happy to share, as many did with us during the design process. This slide is a quick overview of the footprint of the NWSC with the cooling tower, water tank, and cooling distribution system layout. The water tank is a 60-foot tall tank containing 135,000 gallons of water with a nitrogen blanket atop the water line. The NWSC design has 2 modules, A and B. Module A was built out as shell space initially, and we are currently in the process of occupying Module A. This design feature puts Module A and Module B a decade apart so as to stagger the age of the infrastructure components between the 2 modules. The NWSC is a 24/7 operation and is staffed as such. There are several factors that support this decision, as well as the ones stated in this slide. This decision has proven to be very effective as incidents have been caught and minimized very early on. We are very proud of the teams at the NWSC. They are very professional and dedicated to the mission of the facility, the Computational and Information Systems Lab, the National Center for Atmospheric Research, and the University Corporation for Atmospheric Research. To automate or not to automate? That is the question, and is the fundamental question that must be asked in the design phase and fine-tuned throughout the operational process. Some will say it should all be automated, and some are not willing to stake all the facility performance on automation. I think everyone can agree that automation is a good thing, but bad sensors can send bad information to a system that will then potentially make very bad decisions. Having manual override capability is very important, in my opinion, so human intervention is possible in a scenario where conditions or components are sending the system in a bad direction. With that, I will turn it over to Michael to get to the substance of the paper, the problems discovered, and how we went about solving them.
Thanks, Gary, for the great explanation of how the NWC was conceptualized and what allowed us to move into the construction and operation phase. My name is Michael Kercher, and I'll be reviewing the rest of the content of our paper. As the design was becoming finalized, a few key points were emphasized. These included the goal of a versatile design with a low PUE of 1.2 to 1.5. There was also a strong desire to use LEED best practices and try to obtain a LEED Gold certification, almost unheard of for data centers in the early 2010s. These key points were then implemented using a very unique design approach. Design teams with data center specific experience were utilized to help build the framework for a world-class, efficient center worthy of the National Center for Atmospheric Research's mission and taking into account their place in building a greener, more eco-friendly world. Through these higher level design steps, a more Rocky Mountain, Front Range regional engineering firm was brought in to make sure the efficiency of the local climate was properly utilized and capitalized upon. There were also subject matter experts, specifically with mechanical control experience, who were also consulted and brought into the fold to assist in the creation of the complex sequence needed to implement the design criteria established. Finally, the NSF review panel process was also used as a collaborative effort to use the lessons learned from the great depth of experience represented within that team. Commissioning plans were also developed through an extremely collaborative process. The use of peer input through the Energy Efficiency High Performance Working Group, a High Performance Computing Operation Review Consortium, third-party vendors, and the in-house expertise, an extremely in-depth commissioning plan was developed to ensure the NWC facility would be ready for the first HPC deployment. To follow up more about the geographic location of Cheyenne, Wyoming, and the optimal conditions for free cooling, specifically airside free cooling, I want to refer you to this map developed by the Green Grid paper number 50 to illustrate the amount of hours projected for free cooling per year. Where Cheyenne is located on the map provides an estimated 8,000 hours or more of free cooling availability, making Cheyenne, Wyoming a prime geographical location for HPC activities. Out of the design process, the following metrics for the NWC were created. The HPC chilled water would be provided at 18 degrees Celsius with a chilled water flow potential of up to 3,000 gallons per minute. The computer room would also maintain 40% humidity, and the room air temperature would be controlled to 22 degrees Celsius. These matrices developed were based on providing an efficient cooling system that would be extremely versatile and allow for future expansion. There's much to be said about control strategies and the approach a specific data center may use. Some data centers try to use the least amount of hardware and technology as possible, where there may be only a fan, coil, and a valve to perform the cooling for a center. Other centers use automation to the full extent possible, where AI is using complex algorithms to determine the most efficient way to run the facility, and sometimes even how to schedule the HPC users to help make use of peak efficiency times. Ultimately, an HPC data center has to have some form of complexity built into it, as these facilities are more susceptible to huge load swings, and some are located in areas where the utility providers expect these types of swings to happen outside of peak usage hours, or even expect some kind of cogeneration where the mechanical system has to be extremely sophisticated to accommodate these requirements. There is also an industry-wide approach to make these systems as efficient as possible to limit utility costs. This means data needs to be collected from a variety of sources, compiled, and then control decisions need to be made to provide efficiency, redundancy, and resiliency. These ideals are always pulling at each other, where to be more efficient may cost redundancy or resiliency, or where more resiliency will cost efficiency. Determining the best approach to these decisions inherently creates complexity. The NWSC tried to balance all of these ideals as they approached the final design. As this step was winding down, air cooling was the more prevalent technology. So to be as versatile as possible, the NWC Module B computer room was outfitted with the ability to cool 4 megawatts of load fully through air or through a mix of water and air cooling. A N+1 approach was used in conjunction with the latest proven design approaches to help make the NWC mechanical system as efficient as possible. As with all control systems, a KISS, or Keep It Simple Stupid approach was used, taking into consideration the mission, total cost of ownership, TCO, and other base requirements for the center that will be reviewed next. Some of these base requirements were associated with costs. First cost is the ultimate initial investment in instrumentation for extensive monitoring and controls. Will there be enough efficiency gains through this investment to pay for the hardware associated with the data collection and control system? This is normally determined through a total cost of ownership evaluation. Another requirement that was considered is operational costs. This related to the requirement for energy efficiency and management of this efficiency. Does more manual control equate to the need for more on-site personnel? And do all aspects of the control system need to be automated to make the most energy efficient system possible? There are also things like operational risk. Generally, we expect an automated control system to be better at minimizing risk. Certainly a control loop isn't going to accidentally turn a valve the wrong way, but can an automated control loop be aware of enough of the operational parameters and specific circumstances to properly change a significant portion of a system to an alternate operation mode? This is harder to determine the total cost of ownership, but a rough idea TCO should be completed. And then finally, reconfiguration. Control loops that are regularly used will be retuned as systems are changed or modified, largely through the efforts of a competent hands-on operation staff. But what happens when the control sequences are infrequently used? How much of the loop dynamics may have changed, and will it still be able to make the required changes properly? What about system expansions and modifications on the IT side? What must be accomplished to ensure the control loop will be able to function as needed based on the new loads? The design and equipment list was developed using the requirements previously discussed for the NWC. A parallel piping condensing water system was designed to feed the two 750-ton, 18 degrees Celsius supply temp free cooling heat exchangers and the single 1,000-ton, 18 degrees Celsius supply temp centrifugal chiller that are responsible for cooling the NWC computer equipment. It is an interesting note that the centrifugal chiller was not redundant due to the low demand, roughly 80 hours out of the 8,760 annual hours. There are also two 90-ton, 7 degree Celsius supply temperature scroll chillers used for comfort cooling and dehumidification in the facility. These are not necessarily associated with the cooling of NWC IT equipment. The large 1,000-ton centrifugal chiller was designed to utilize the large 135,000-gallon 18 degrees Celsius chilled water tank during the transition between heat exchanger to chiller. During commissioning of the system, a major incident occurred within the chilled water piping. A control loop driven change in the three-way valve position that allowed flow through the reserve chilled water tank caused a significant event that could have either been cavitation or water hammer. This event was felt through the entire facility, and staff determined that some parts of the piping system physically displaced as much as 6 inches. The root cause of the problem was not determined specifically. Hindsight tells us we should have, but the demands of the schedule during commissioning caused it to become a second-tier problem. In any case, the team was now aware and concerned that there could be issues with the transition between the two cooling modes that could cause damage within the plant. Manual switchovers between the modes had been accomplished with no issues resulting, and it was determined that a manual switchover mode should be explored and implemented. As part of the switch to chiller implementation, the alarming and control logic was left in place, with only the automatic control to command the switch removed. This resulted in a tiered alarming system to help the operator on shift determine if switching to chiller was appropriate given the load of the system, the current state of the chilled water loop, and the outdoor conditions. Ultimately, the potential of switching to chiller only applied to roughly 3 to 5% of the year. The amount of year where the switch was imminent was roughly 1 to 2% of the year. And finally, the actual time where the chiller was required is only 1%, or roughly 87 hours per year. With the incredibly limited amount of time that the chiller was needed, the manual switch between modes seemed appropriate, especially in light of the fact that the NWC PUE was 1.2 when in free cooling, and the PUE was 1.3 when in mechanical mode. A manual switchover, even prematurely, would not interfere with the overall PUE for the year. Here's a quick look at the intervention needed to be performed by the operator when switching between modes. There's only one point that needs to be manipulated. The net sys mode 65F point gets commanded from free to mechanical cooling when the chiller is needed, and then commanded back from free to mechanical when the chiller is no longer needed. All other parts of the transition is automated. It is only the decision to move between modes that is manual. Yellowstone was installed in 2012 as the initial high-performance compute system at the NWSC and had an average power draw of 1.2 megawatts with a peak performance of 1.504 petaflops. The total footprint for this system was 79 racks. This HPC system was cooled with rear door heat exchangers, capturing the heat through a large coil mounted to the back of the rack. Cheyenne was installed in 2017 as a second-generation supercomputer. The average power draw for this system is roughly the same as Yellowstone at 1.3 megawatts, but the performance was increased to 5.34 petaflops. The total footprint for this system was also dropped by a third, for a total of 26 racks. The HPC system was cooled by a CDU, cooling distribution unit, with a cooling subloop. The system performed heat capture at the chip level for a majority of the system. Throughout the operation of the Yellowstone HPC system, the NWC plant experienced no major issues during all manual transitions between the free and mechanical cooling systems that were performed. As Cheyenne was being commissioned, all initial transitions between free and mechanical cooling showed no sign of major issues. However, as the HPC system aged, a few problems arose within the CDU subloop, where equipment inside the racks were getting dangerously close to their upper limit operating temperature ratings. When mechanical cooling was needed, the process was very serial. The chiller valves would open, the heat exchanger valves would immediately close, and then the chiller would go through its startup sequence. During the startup sequence, the NWC 18 degrees Celsius chilled water loop would raise in temperature to 21 degrees Celsius for up to 5 minutes. This rise in temperature was enough to affect the CDUs, and some HPC hardware failed. As the NWC staff were determining the root cause of some of the HPC hardware issues, the facility team again decided to approach the problem through collaboration. During the operation of the MDC, a very strong relationship had formed between the operations staff and the control contractor, Johnson Controls. The facility personnel also brought this problem to the EE-HPC working group team to get input from their colleagues and to learn how other sites have handled these types of situations. The working group suggested that the NWC may want to look at running their cooling system in parallel while the chiller is starting up, explaining they had seen success with this approach at their and/or other sites. After reviewing the possibility of these changes with the NWC partner control vendor, it was determined that the condensing and chilled water system pumps could support the flow of running the systems in parallel. All free and mechanical cooling equipment would run in parallel during the first 5 minutes while the chiller started up. There were also changes done to bypass valve control associated with the loop and verification of DP requirements for the large 1,000-ton centrifugal chiller. I wanted to go over some of the hard data we have to show what we feel is a successful change in programming and sequence. These graphs show the supply temperature provided to the CDUs from the NWC chilled water system. The top graph shows the temperature reaction before the changes were done and the modes were ran in a serial manner. The system rises from 18 to 21 degrees Celsius and then back down to 18 degrees Celsius over a span of roughly 10 minutes, and the system takes some time to recalibrate. The lower graph shows the post-programming change transition. The temperature of the loop still spikes to 21 degrees Celsius, but it is quickly brought back down to 18 degrees Celsius within 2 minutes. To the NWC team, this shows that the change successfully caught the load between modes much quicker as compared to the original sequence. This set of results is based off of facility loop chilled water flows through the CDUs. In the top graph, you can see that during the original sequence transition, the flow would increase slightly during the change between cooling modes, and then it would fall sharply back down. After adjusting the programming associated with our chilled water loop bypass valves to better handle the systems running in parallel, the lower graph shows how we increase flow during and after the transition to all the CDUs. This has helped ensure the heat is properly taken out of the system and solid flows are always available. The final set of results relates to the CDU valve position. During the original sequence shown on top, the valves would skyrocket to 100% and stay there for some time to try to evacuate as much heat as possible from the system. In the lower graph that shows our transition post changes, the valves open to 100% but only momentarily, proving that the heat is dissipating from the CDUs more efficiently after the change. When looking at designing the control system for a complex HPC facility, many different factors play into deciding what level of automation should be implemented into the system. Some of these factors include mission, budget, available staffing, location, and available utility supply. If there are approaches to the data center design where multiple cooling resources are deployed and used, understanding how often these modes will be needed is critical, and understanding and deciding how to transition. The NWC originally planned on a fully automated system, but found a primarily automated with infrequent manual mode changes to be the best setup for the site. Some of our reflections related to first cost are that the NWC may have been able to save some design and programming costs had they a crystal ball, but there would not have been significant other capital savings as the control elements and the instrumentation were still required and being used to track NWC's efficiency and low PUEs. Some of the reflections relating to operational costs are that the NCAR had a commitment to staff the facility 24/7 from the beginning, so options were available to make things more manual when switching between free and mechanical cooling based on the limited number of times this process would be needed. The team's operational risk reflections are that the system upset risk is real, and that the NWC's change to manual transitions is felt to have provided a more stable system overall, especially as the IT loads change. Finally, reconfiguration is constant. The NCAR IT loads have doubled since the initial startup of the site, and it continues to go through changes and upgrades across the full IT hardware kit. Simplifying operations and including a few manual transitions has supported these reconfigurations well. Our feeling is this problem could relate to other sites as supply-side chilled water temperature set points rise, and free cooling becomes an option for areas that have higher humidity than what is normally thought of as ideal for free cooling practices. The NWC plans to continue this research and to continue to make the systems better over time. Continuing strong partnerships with vendors and making sure that staff are well trained and feel ownership in the processes help make sure change and adaptation is embraced. Another huge part of making sure the NWC continues to be successful is to continue to be involved in working groups like the EEHPC. This collaboration has been a huge help in understanding the industry's best practices as it relates to control systems and HPC cooling. I appreciate you viewing our presentation video. Thank you very much, and have a great day.